the critical function is a numerical way for us to detect whether we are working in a Euclidean or a non-Euclidean geometry. And it's designed to measure basically when there is only one parallel line parallel to a given line through a given point, and when there's more than one. So we start with its definition. Definition 109. Given a right angle ABC, we can let K be the set of all angle measures where we're looking at the measure of angle ABD, where D belongs to the ray AC. The picture of what's going on here is that we have a right angle like this with a point A, point B, point C somewhere here. And then basically what we're doing is we're looking at the angle measures that we get when we take all the rays that intersect the line BC. And so we can see that as we increase our angle measure, the angle BAD, we've got all these various D's here on the ray BC. Oh, sorry, I wrote AC down here. This should be BC. As we look at all of these angle measurements, our rays are getting sort of flatter and flatter and flatter and flatter. If we look at all of those, then we get this set K that tells us all of the angles. Pardon me. Which give us a ray that makes this happen. The critical function of the angle ABC is denoted little c of the pair of the triple ABC, and it's defined to be the supremum of K. You look at all these angles that are made by B to A to D, where D is some element of the ray BC, and you get a bunch of angle measurements there, and you take its supremum, and that's going to give you K. Now, we always have that the critical function of ABC is always greater than 0, since the measure of angle BAC is in K, and the critical function is the supremum of K, and the measure of angle BAC is positive, so the supremum of K has to be positive. Now, we don't have to, it turns out, work with every right angle separately. First of all, you note that, of course, that the critical function of the angle ABC certainly doesn't depend on the point C. We could change this point C for any other point on the ray, and it wouldn't change the ray BC at all. So the point C certainly doesn't matter. But it turns out that the position of the angle doesn't matter either. It turns out the only thing that matters is this distance, is the distance from A to B. So Theorem 110 says that if the distance from A to B is equal to the distance from A prime to B prime, then the critical function of ABC is equal to the critical function of A prime, B prime, C prime. And this can be easily seen by showing that if you have your right angle A, B, C, and another right angle over here, A prime, B prime, C prime. Then if I look at some number that's in the K set for my left angle, that's going to be given by some point D over here. And that gives us an angle measure R here. So the proof of this basically goes that if R is in K, then there exists a D in the ray BC such that the measure of angle BAD equals R. So that tells us that we can let D prime be in the ray B prime C prime such that B prime D prime is congruent to BD. If we do that, then we get some point D prime over here, and we're told that B prime D prime is, we can construct it so that B prime D prime is congruent to BD. Now we can construct the ray from A prime through D prime. Now by side angle side, we have that the triangle ABD is congruent to the triangle A prime, B prime, D prime, which tells us in particular that this angle at A prime rather, is congruent to the angle at A. So that tells us that R belongs to K prime, where K prime would be the set of angles defining the critical function for the A prime, B prime, C prime angle. This tells us that K is a subset of K prime, but of course we can reverse all of these arguments to show that K prime is also a subset of K. So in fact, K and K prime are equal sets, and therefore their suprema are equal. So what this means is that we usually refer to the critical function C of A, C of little a, to mean C of any right angle ABC with the distance from A to B being little a. So the critical function, in fact, depends only on the length of the segment AB, not on anything else. In particular, not on where in your geometry the points A and B live. Now, one thing that's kind of obvious from the construction, but that we want to have recorded for use in later results, is Theorem 111. So let's let angle ABC be a right angle, and E a point on the C side of the line AB. Then the ray AE intersects the ray BC if and only if the measure of angle BAE is less than the critical number of the length AB. All right, so let's see what the setup here looks like. We've got our right angle AB C, and we've got a point E over here. What this theorem is telling us basically is that if we were to draw the ray over here with a measure equal to the critical function of a, of little a, where little a is the distance from A to B, then any rays that you construct that sit below the critical function will intersect the ray BC, and any rays that sit on the critical function or have that angle measure equal to the critical function or above will not intersect the ray BC. So this ray with an angle measurement equal to the critical function gives the boundary between the rays that will intersect BC and the rays that won't intersect BC. So possibly the most important result here is, the most important part of this is that the ray coming off of A, which has an angle measure exactly equal to the critical function, doesn't intersect the ray BC. So let's see how the proof of this goes. So let's say if the measure of angle BAE is less than the critical function of AB, well, the critical function was the supremum of a set, and any number less than the supremum of a set has to be less than some element of that set. And so the critical function of AB is equal to the supremum of the set of angle measures BAD, where D belongs to the ray BC. So that means that there exists a point D in the ray BC such that the measure of angle BAE is less than the measure of angle BAD. So that tells us that in this case there's some point D over here where the angle BAD is greater than the angle BAE. So now, by the crossbar theorem, the ray AE intersects the ray BD, or the segment BD, which is itself a subset of the ray BC. So that proves that if the measure of BAE is less than the critical function, then that ray AE will intersect the ray BC. Now, let's go the other way. Now, if the ray AE intersects the ray BC, we may assume that actually that E is in the ray BC for convenience, and then let D be a point such that D is on the other side of B from on the other side of E from B. So now we have that the measure of angle BAD is greater than the measure of angle BAE, but we also have that the critical function of AB has to be greater than or equal to the measure of angle BAD, because the measure of angle BAD is one of the numbers in the set that the critical function is the supremum of. So that tells us that that Theorem 111 holds that the angle that's formed here with the forming the angle, with an angle measure of the critical function does not intersect the ray BC, but it's sort of the closest one that does. Any ray that's in the interior of that will intersect the ray BC. All right, so now if we have the following setup, if we take our right angle A, B, C, and then we take the ray AE in such a way that the line AE is actually perpendicular to the line AB, then we certainly have that in this case the line AE is parallel to the line BC. So this means that the critical function of AB has to be less than or equal to the measure of angle BAE, which is 90. So in particular, this shows that the critical number of A is less than or equal to 90 for all A. And in fact, we already showed that it's positive. So we have that the critical number is always greater than 0 and less than or equal to 90 for all A. Furthermore, if the parallel postulate holds, then the line AE is the only line through A which is parallel to BC, which means in particular that if we take any ray where the angle BAF, now let's say, is less than 90, then the ray A, or the line AF and the line BC have to intersect, and because the angle BAF is acute, we can actually show that they have to, that the ray AF has to intersect the line BC. So that means that if the parallel postulate holds, then in fact C of A is equal to 90 for all A. So the critical number has to be equal to 90 for every number A if the parallel postulate holds. And certainly if the critical number was equal to 90 for all real numbers A, then that would also mean that the parallel postulate holds. Now, there are a few things that we're going to want to look at about how the critical function behaves when you change A inside. Now, the next theorem, we're not going to run through a proof of. We'll just sketch out the diagram and see how it goes. So, Theorem 112 tells us that the critical function is a decreasing function. Tells us that if A prime is greater than A, then C of A prime is less than or equal to C of A. So the picture looks like this. Let's say we have B, we had A, and then we have A prime somewhere up here, where the distance from B to A prime is little a prime, and the distance from B to A is little a. So now, let's take this ray here that comes off of A and has an angle measure of C of A. And then let's take the, let's also take the ray off of A prime, which has the same angle measure C of A. And let's give these lines a couple of names. Let's call this first one L and the second one L prime. Now, we have that, we need the point C down here. We have that L is parallel to the line BC since, or let me call this E and E prime, since the measure of angle BAE is equal to the critical number. And if this measure is equal to or greater than the critical number, then the rays don't intersect, and therefore these lines won't intersect. So L is parallel to BC, and then this A prime is going to, notice that the A prime and the B are on opposite sides of the plane, or on opposite sides of the line L on the plane. So the lines L prime is parallel to L, since we have corresponding angles equal. We have the corresponding angles BAE and BA prime E prime. Those are congruent, and we know that if we have two corresponding angles congruent, then the two lines are parallel. That holds even without the parallel postulate. It's the other direction that required the parallel postulate. And so, since A prime and B are on opposite sides of L, we must have that L prime is parallel to BC also. The line BC lies entirely on one side of L, the line L prime lies entirely on the other side, and therefore they can't intersect each other. So that means that the ray A prime E prime intersect BC is empty. So that means that the critical number of A prime has to be less than or equal to the critical number, or less than or equal to the measure of angle B A prime E prime, which is the critical number of A. This is the idea behind Theorem 112. So it's sort of like what we were seeing with the diagrams in the Poincaré model, is that as you increase distances, the critical function, which in a sense measures how non-Euclidean you are, gets more and more extreme. So now notice that this is only a weakly decreasing. So this is just saying that the critical numbers can't be getting any bigger as you increase the distance from B to A. They can only get smaller, but they might stay the same. In fact, if the parallel postulate holds, then the critical number is just always 90. But let's consider what happens if the critical number is less than 90 for some value of A. That's what Theorem 113 says. Theorem 113 says that if the critical number of some distance is less than 90, then the critical number of A over 2 is less than 90. In particular, if C of A is less than 90 for some A, then C of A is less than 90 for all A. Let's start by talking about this in particular bit at the end. This in particular bit that says that if the critical number is less than 90 for some distance, then it has to be less than 90 for all distances, is a combination of the Theorem 113, or the first part of Theorem 113, and Theorem 112. So for the in particular, if C of A is less than 90 and B is any positive number, We can say that by the first part of Theorem 113, C of A over 2 is less than 90, C of A over 4 is less than 90, etc., etc. And so we can get that C of A over 2 to the n is less than 90, where A divided by 2 to the n is less than B. Given any positive number, there's some number n such that A divided by 2 to the n is less than B. And then, by Theorem 112, since B is greater than A over 2 to the n, the critical number of B is less than or equal to the critical number of A over 2 to the n, which is less than 90. So that's how the in particular piece goes. Let's finish the proof and then talk about the implications of this. So what we're going to do is we're going to set up the following diagram. BAC, have A prime here, so that this distance A, the distance from B to A is A, and the distance from B to A prime is A over 2. Now let's let L be the line that goes through A prime and is parallel to the line BC. And then let's take the line or the ray coming off of A, and I want to leave this a little bit general here, and with the measure C of A. Let's see. We'll give this a point E so that we can talk about that. All right. So, given the setup to the left, let's consider a couple of cases. If the ray AE intersect L prime is empty, then if we look at the setup of A prime, and some point F out here on L prime, this tells us that in this case the C of A is greater than or equal to the critical function of A prime F, which is equal to the critical number of A over 2, because that's the distance from A to A prime. So in this case, we would have that C of A over 2 is less than 90. So that gives us what we want. So assume that the ray AE does intersect the line L prime at the point F. So let's see what that gives us. Well, I guess I have to move my point F. Okay, so now we want to try to show that the critical number of A over 2 is not 90, and we're going to do that by contradiction. So if the critical number of A over 2 is equal to 90, then let's let G be a point on the ray AF, which is on the other side of G. And then the ray A prime G must intersect the ray BC. Because under this setup now, the measure of the ray B, or the angle BA prime G, is going to be less than 90. And we've assumed at this point that the critical function of A prime is, of A over 2 is equal to 90. We're going to try and come up with a contradiction. So let's redraw this in a slightly more extreme way so that we can see how the contradiction is going to arrive. So we've got the points A prime, B, C. We had the line L prime. We had the ray AG. Where this G came from being on the other side of this ray AF. And we have that this is the critical function of A, where A is the total distance from B to A, and this is A over 2. And we want to show why this gives us a contradiction. And it's going to be via the Posh postulate. So, by the Posh postulate, let's label this point H over here, where the ray A prime G intersects the ray BC. Since the line AG intersects a side of triangle BA prime H, it intersects the segment BA prime or the segment BH. But since G is not in the line AB, which is the same as the line A prime B, that tells us that the ray AG does not intersect the segment A prime B, and so we must have that the line AG intersects the segment BH. Now we can use a plane separation argument to show that by plane separation, this means in fact that the ray AG must intersect the segment BH. This is basically since G and H are on the same side of the line AB. But this is a contradiction. Since the segment BH is a subset of the ray BC, and the measure of angle BAG is equal to the critical number of the distance BA. So what we have is that the critical, the assumption that we made that gave us this contradiction was that the critical number of A over 2 was equal to 90. So this shows that the critical number of A over 2 can't be equal to 90 if the critical number of A is less than 90. So that finishes Theorem 113. Now, the in particular part of Theorem 113 is sometimes called the all or none principle. Now, what this means is that either C of A is equal to 90 for all A, or C of A is less than 90 for all A. Now, the critical function being equal to 90 was equivalent basically to saying that the parallel postulate holds, that the parallel postulate is true, that there's only one line through a given point parallel to another given line. And so this is saying that either such a statement holds for all lines and all points, or it holds for no lines and no points. So, in particular, what this means is that if the parallel postulate does not hold, then given any line L and any point P not on L, there are infinitely many lines L prime containing P and parallel to L. So without this principle, then if we didn't know the parallel postulate held, or if we assumed the parallel postulate didn't hold, that could mean any one of a number of things. It could mean that, well, maybe usually it does, but there's one specific line and one specific point where you get two parallel lines instead of one. Maybe it only breaks a little. No, the all or none principle says that if the parallel postulate either holds completely or it fails completely. Either parallel lines through points are unique everywhere, completely unique everywhere, or they are completely non-unique absolutely everywhere. This really does mean that it's impossible for a geometry that satisfies the first axioms that we've had up through side angle side. It's impossible for such a geometry to be sort of Euclidean in some places and non-Euclidean in some other places. It's either completely Euclidean or completely non-Euclidean. The question of being Euclidean or non-Euclidean is a universal property. And what that means is that given sensitive enough equipment, if one lives at any point in a non-Euclidean universe, one should be able to detect it. Now, an interesting aside here, we don't actually know whether we live in a basically Euclidean universe or not. The difficulty is that while it's conceivably possible to prove that you live in a non-Euclidean universe by showing that there do not exist parallel, or that you don't have unique parallel lines, or perhaps by showing that you can construct a triangle where the sum of the interior angles is less than 180, it's not actually possible using scientific instruments to prove that you do live in a Euclidean universe. And that's because there's always some margin of error. Any physical instrument has a certain precision to it. And so if the part of the universe that you, or if the universe that you live in happens to be large enough that the differences between Euclidean and non-Euclidean are very, very, very small over short distances, then you won't necessarily be able to detect it. There have been experiments doing this where where scientists and mathematicians have constructed giant triangles, like between three different mountaintops, and measured the angles involved to see whether they added up to 180. And they always have. but that's always to within a certain margin of error. And if the actual angles involved do not add up to 180, but by a small enough amount, we won't be able to detect it. So the upshot of this is, which is perhaps a little bit unsatisfying, is that while we may be able to, at some point in the future, prove using scientific instruments that we live in a non-Euclidean universe, we'll actually never be able to prove completely for sure that we live in a Euclidean universe. All right, so at this point, we want to start talking about non-Euclidean geometry. So we are now going to take a new axiom. Instead of the parallel postulate, we are now going to talk about the hyperbolic parallel postulate. The types of geometries that we're going to look at now that satisfy all of our hypotheses or our axioms up through side angle side, but fail the parallel postulate, are known as hyperbolic geometries. And that's what gives the name to the next axiom we're going to have, the hyperbolic parallel postulate, or HPP. The hyperbolic parallel postulate says basically that we live in a that the parallel postulate doesn't hold. Or more precisely, given any line L and point P not on L, there are infinitely many lines L prime with P belonging to L prime and L prime parallel to L. So it's another way of stating this would be that the critical function is less than 90 for all distances, or simply that the parallel postulate doesn't hold, that there exists at least one point and at least one line where there are two lines that go through that point parallel to the given line. But we'll go ahead and give it its strongest form as implied by the all or none principle before. Now, in the hyperbolic parallel postulate world, in the hyperbolic geometry, the condition of being parallel is no longer special, because there are infinitely many points through a given line that are parallel, through a given point that are parallel to a given line. It doesn't really tell us much for two lines to be parallel to one another. So what we do want to do is introduce a new type of condition that is stronger and actually gives us things to work with in the hyperbolic geometry case. So we'll go to definition 114. Given rays AB and CD such that the lines AB and CD are parallel, and such that B and D are on the same side of the line AB, we have the following. We call the ray AB union the segment AC union the segment CD an open triangle. Denoted triangle BACD. So the picture of this to keep in mind is something like the following. BACD. Now the point behind an open triangle is that it's not a triangle. The rays CD and AB do not intersect. We've assumed that the lines AB and CD are parallel to one another, so we do not have a We do not have a triangle here. They don't intersect, but it turns out that they are going to behave in some ways like triangles. We can use some of the same theory behind them. If triangle BACD is an open triangle, and the two angles of it are congruent, so angle BAC is congruent to angle DCA, then the triangle BACD is called isosceles. Of course, we don't have a notion of side length here, except for the segment AC, but we can talk about the angles inside and define isosceles using congruence of angles. A bit of notation, if R and R prime are rays, and R is a subset of R prime, or R prime is a subset of R, we write that R is equivalent to R prime. So this is the same notation as the similarity relation between triangles, but because we're working with rays rather than triangles, there shouldn't be any confusion there. So for instance, if I put the point A prime here on the diagram, then the ray AB is said to be equivalent to the ray A prime B. So as long as one is a subset of the other, then we say that the two rays are equivalent. Sort of, they point in the same direction. And then we also can say we also have a notion of equivalence for open triangles. So given open triangle BACD, if we have that the ray A prime B prime is equivalent to the ray AB, and the ray C prime D prime is equivalent to the ray CD, then we say that the triangle BACD is equivalent to the triangle B prime, A prime, C prime, D prime. So this sort of situation would look like the following. If we have the two triangles, the two open triangles BACD and B prime, A prime, C prime, D prime, as in the diagram here, we will say that those two triangles are equivalent to one another. They don't include all the same points, but they are similar in that their two ray sides point in the same direction, and equivalent open triangles wind up sharing many properties. Okay. The next result is the next definition rather is going to be in many ways a replacement for the notion of parallel. As I mentioned, being parallel is no longer special in hyperbolic geometry, but we do have a notion of critically parallel, which is related to the critical function. So this is continuing the definition 1.14. If triangle BACD is an open triangle, and every interior ray of angle ACD intersects the ray AB, then we say that the ray CD is critically parallel to the ray AB, and we write that CD is critically parallel to AB. So now we use just a single vertical bar rather than a double one. So the picture of this here is that we've got some open triangle. We've got the points B, A, C, D. And the point is basically that this ray CD does not intersect the ray AB, but any inside angle would. If I took any ray that lies in the interior of this angle ACD, then it would intersect the ray AB. So in other words, this angle CD has come down as close to the ray AB as possible without actually touching it. If I take anything even a little bit more inside, then this ray will intersect the ray AB. And then if triangle BACD is an open triangle and the ray CD is critically parallel to the ray AB, then we say that the triangle BACD is a closed triangle. So this terminology is a little bit counterintuitive at first. A closed triangle is a special kind of open triangle. We can see some of what's going on here if we look at some examples using the Poincaré model. So if I try drawing an open triangle, I'm going to need some segments and some rays. So I'm going to sketch in a few Poincaré lines here. And if we have this set up, then, for instance, we could look at the points B, A, C, D, and then the union of these, the segment AC and the rays AB and CD is an example of an open triangle. Now, in this case, triangle BACD is open but not closed. And I know it's not closed because I could draw in a ray that comes in from C that it's an interior ray to the angle ACD, but it doesn't intersect the ray AB. If I want to construct a closed triangle, then basically what I have to do is I have to construct the ray that goes like this, where the green circle and the circle containing AB don't intersect in the Poincaré model, but they do intersect at the boundary. That there is a point out here on the boundary where those two Euclidean circles intersect. So if we call this point E, then the triangle BACE is a closed triangle. And it turns out that closed triangles, even more than open triangles, behave like ordinary triangles in hyperbolic geometry. Now, let's let's see what we can say about critically parallel rays and closed triangles. So Theorem 115 says that the most efficient way of stating this is the following. If the ray AB is critically parallel to the ray CD, and the ray AB is equivalent to the ray A prime B prime, and the ray CD is equivalent to the ray C prime D prime, then the ray A prime B prime is critically parallel to the ray C prime D prime. So the principle here is that the notion of being critically parallel doesn't depend on where you start the ray. If we start with two rays that are critically parallel, like AB and CD here, and then we decide to take any equivalent rays, such as the C prime D prime here, or maybe an A prime B prime like this. Well, all we've done basically is change where the rays have started. But being critically parallel is a statement about what happens in the long term. In the Poincaré model, it's a question about would the lines intersect if we included the boundary of the model here. It doesn't really depend at all upon where they start. And a related theorem, 116, says that being critically parallel is a symmetric relation. It says if AB is critically parallel to CD, then CD is critically parallel to AB. And this is actually less trivial than it immediately looks. If we recall back and remember what exactly it means to be critically parallel, which we need to make sure to do, to be critically parallel means that if I take any interior angle here, then or any interior ray of the angle ACD here, then that will intersect the ray AB. It's not immediately obvious that such a statement proves that if I take any interior angle of the ray CAB, that I'll necessarily intersect with the ray CD. One could imagine a situation where any interior ray of the angle ACD has to intersect with the ray AB, but not the other way around. But Theorem 116 says that this can't happen. Now, the proofs of Theorem 115 and 116 are somewhat technical. They're long. They're sort of fiddly. We're not going to work through them here, so that we can get to some of the more interesting results. But the notion of being critically parallel is, as I said, in many ways a replacement for the notion of being parallel. Being critically parallel has a sort of uniqueness aspect to it, as long as we consider it's unique up to equivalence of rays. All right, so as I said just now, Theorem 117, given a ray AB and a point C that's not on the line AB, there is a unique ray CD such that the ray CD is critically parallel to the ray AB. All right, so let's see how this proof goes. Let's actually do this one. We've got A, we got C, and we're trying to construct we're trying to show that there is only one ray CD that is critically parallel to AB. And for this, we're going to use the critical function. So let's let A prime be in the ray AB such that the line A prime C is perpendicular to the line AB. Let's come down like this, take this point A prime here. The point now is that we're back in the situation that we were looking at before with the critical function. So now let CD be the ray with D on the I've drawn my diagram here as if B is on the other side of A prime from A, but that's not necessarily the case. So let's let B prime be in the ray AB such that the ray A prime B prime is equivalent to the ray AB, and let D be a point on the B prime side of the line A prime C such that the measure of angle A prime CD is equal to the critical number of the distance A prime C. So we're going to do this. We are going to take the point D over here, and this angle that we construct has measure exactly equal to the critical number of the distance A prime C. Now, we claim or rather, from all of our work on the critical function earlier, we have that the ray CD is the unique ray such that the ray CD is critically parallel to the ray A prime B prime. And so the ray CD is critically parallel to the ray AB because the ray A prime B prime is equivalent to the ray AB. So we use the critical function here to construct the unique ray CD that does what we want. Now, Theorem 117 is sort of the hyperbolic geometry analog of the parallel postulate, talking about there being a unique ray that is critically parallel to a given ray with the point C at the vertex. There are some other analogs of well-known results from either Euclidean geometry or general geometry that we can work on as well. So, for instance, Theorem 118 is the analog of the statement in Euclidean geometry. In Euclidean geometry, if one line is parallel to a second line, and the second line is parallel to a third line, then the first and third lines are parallel. Well, the same thing is true if you replace lines with rays and replace parallel with critically parallel. So Theorem 1.18 says that if the ray AB is critically parallel to the ray CD, the ray CD is critically parallel to the ray EF, and the ray AB is not equivalent to the ray EF, then AB is critically parallel to EF. Let's see the proof of one case of this. There are two cases. One of them is a little easier than the other. That's what we'll do. So case one, let's suppose that A and E are on opposite sides of the ray CD. So the picture that this would look like is approximately the following. So we've got our ray AB, which is critically parallel to the ray CD, which is, again, critically parallel to the ray EF. Now, without loss of generality, we may assume that C actually lies directly in between A and E. And the reason for that is that we know that A and E are on opposite sides of the line CD. That should be the line CD up here. Which means that the segment connecting them intersects with the line CD at some point. If we just replace whatever the point C was before with the point that lies in between A and E, that's going to give us a ray that is equivalent to the original ray CD, and because being critically parallel doesn't care if you replace one ray with an equivalent ray, then all of our statements still hold. And so if we prove the theorem in this situation, well, then at least this case of it will be solved. Now we want to show that the ray AB is critically parallel to the ray EF, which means that we want to show that if we take any interior ray of the angle EAB, then that has to intersect the ray EF. So let's go ahead and do that. Let's let the ray AG be an interior ray to the angle EAB, which of course is the same as the angle CAB. Now, since the ray AB is critically parallel to the ray CD, we know that the ray AG must intersect the ray CD at a point H. So, because the ray AB is critically parallel to the ray CD, this interior ray AH that we've AG that we've got must intersect the ray CD at some point. We'll call it G. But now, we'll call it H. But now, we can let I be in the ray CD such that the ray HI is equivalent to the ray CD. So we can choose a point I over here. If you take any point on the line containing a ray, that can always serve as a vertex to a ray that is equivalent to the one that you started with. So now let's let J be in the ray AH such that H is between A and J. So we're choosing a point J over here. Well, now we have that the ray HI is critically parallel to the ray EF. That's because HI is equivalent to CD, and CD is critically parallel to EF. And the ray HJ is an interior ray of the angle EHI, and so that means that HJ intersects the ray EF. But since the ray HJ is a subset of the initial ray AG we came up with, this means that the ray AG intersects the ray EF, and so the ray AG intersects the ray EF. Because AG was any interior ray to the initial angle EAB, this shows that the ray AB is critically parallel to the ray EF. So we have a certain transitivity of critically parallel rays, the way that we do for parallel lines in Euclidean geometry under the parallel postulate. All right. We also have a version of the exterior angle theorem for closed triangles. Theorem 119 has that if triangle BACD is a closed triangle, we cannot expect this to apply to any open triangle, but only closed triangles. If E is another point such that A is between E and B, then the angle EAC is greater than the angle ACD. So let's sketch out what this situation looks like. We have the closed triangle BACD. We have the point E over here, and Theorem 119 tells us that this exterior angle to the closed triangle is greater than this remote interior angle. We could call the angle at C the remote interior angle of the angle EAC. Now, of course, there isn't another angle that that we can work on because the closed triangle is not a true triangle, but we do have this this relationship. The blue angle is always strictly greater than the green angle. So let's prove this. Let's let F and G be such that C lies between F and G, and the angle EAC is congruent to the angle ACG. So we're going to make a copy of the blue angle up here somewhere. Now, at this point, we don't know whether it's interior to the triangle or interior or not, but that's what we're going to figure out. So the first thing that we're going to do is to assume that sorry, we are going to note that in this case, so in this case, we have that the line FG is parallel to the line AB by alternate interior angles. The line AC is a transversal to the lines AB and the lines FG. And because they both have because the angles EAC and ACG are congruent, those two lines have to be parallel. Now, if the angle ACG were less than the green angle, then the ray CG would have to intersect the ray AB, because the ray CD is critically parallel to the ray AB. So let's state that. If the angle ACG is less than the angle ACD, then the ray CG intersects the ray AB, since the ray CD is critically parallel to the ray AB, which is a contradiction, because we've just shown that the line FG is parallel to the line AB. So that tells us that the angle ACG is greater than or congruent to the angle ACD. So it remains to show that they aren't actually equal. So we need to show that that the angle ACG is not congruent to the angle ACD, and then we'll be done. Now, if it were the case that the triangle BACD is isosceles, then in particular, one of the things that means is that the angle BAC is congruent to the angle ACD, and they both have to be acute. In an isosceles closed triangle, both of the angles inside are acute, and therefore the angle EAC is obtuse, because the angle EAC and the angle BAC are form a linear pair. And so in this case also, the angle that means that the angle ACG is obtuse. So that means that the angle ACG is definitely not congruent to the angle ACD. But what happens if the original closed triangle is not isosceles? If the triangle BACD is not isosceles, then we may choose a point A prime in the line AB such that the triangle BA prime CD is isosceles. And the intuitive idea behind that is the following. Let's say that this closed triangle right now is not isosceles. And let's suppose that the angle at A were greater than the green angle at C. Well, then we could move the point A further to the right along AB, which increases the angle at A prime and decreases the angle at C, and eventually they'll basically meet each other. And vice versa, we might go in the other direction in order to match them up. Basically, by moving one end of the triangle back and forth along the ray or along the line AB, we can make the angle on the line AB and the angle at C go in different directions. So we can move them back and forth until we do in fact get them to be get the triangle to be isosceles. So we can get a point A prime there so that these two are isosceles to one another. Now, if the point A prime that we found here is in the ray AB, the way that we have it set up here, then by the normal exterior angle theorem, we have that the angle EAC, which is an exterior angle, or rather, sorry, we want to do it this way. Let me give myself some more room. We have that the measure of angle EAC is equal to 180 minus the measure of angle CAA prime. Now the angle CAA prime, you'll notice, is an interior angle of the triangle CAA prime, and the yellow angle at A prime is an exterior angle to it. So by the exterior angle theorem, we have that the measure of angle BA prime C is greater than the measure of angle A prime AC. But because the measure of angle CAA prime is being subtracted, that inequality reverses, and so 180 minus the measure of the angle CAA prime is greater than or equal to 180 minus the measure of angle B A prime C. Pardon me. We don't want to use the exterior angle theorem just yet. We want to use the fact that we know that the sum of the interior angles of a triangle has total measure less than or equal to 180. So looking at the triangle CAA prime, the sum of all the measures of that triangle are less than or equal to 180, which means if we take 180 minus one of those angles, that has to be greater than or equal to the sum of the other two. So this is going to be greater than or equal to the measure of angle ACA prime plus the measure of angle AA prime C, the other two angles inside the triangle AA prime C. Now this is going to be strictly greater than the measure of angle ACA prime, and now the measure of angle AA prime C is greater than the measure of angle CA prime B. And this is just because the angle AA prime C or rather, the angle CA prime B is acute, and therefore the angle A prime C, which is the forms a linear pair with it, has to be obtuse, therefore has to have a greater angle measure. Now we have that the measure of CA prime B, that's the yellow angle at A prime, that has to have the same measure as the angle A prime CD, because that's how we chose A prime, to give us an isosceles closed triangle here. But by angle addition, we have the measure of angle ACA prime plus the measure of A prime CD has to be equal to the measure of angle ACD, which was in fact what we were trying to show. Now, if A prime is not in the ray AB, then that means that we've got a situation that looks something like this, where we've got the point A prime over here, and a similar sort of argument with combining information together about isosceles triangles always being bigger than acute triangle, obtuse angles always being greater than acute angles, and the angles in an isosceles closed triangle always being acute, etc., all come together to do something similar. So if this is the case, a similar argument holds. All right, now the exterior angle theorem for triangles gives us a lot of power, or did back when we were first looking at these geometric inequalities. It's going to allow us to conclude several important results for hyperbolic geometry as well. So a few of them are as follows. Theorem 120 says that if A prime is greater than A, then C of A prime is less than C of A. Now this is very similar to something we had before, but the theorem we had before only said that the critical function is weakly decreasing. In hyperbolic geometry, the critical function is strictly decreasing. Any greater distance always results in a lower critical number. Similarly, we can get from the exterior angle theorem, Theorem 121, which says that the upper base angles of a Sakari quadrilateral are acute. Now, we have already seen that the upper base angles of a Sakari quadrilateral cannot be obtuse. Their measures have to be less than or equal to 90. But this says that in hyperbolic geometry, they must in fact be specifically acute. In particular, Theorem 121 shows us that there exist no rectangles in hyperbolic geometry. If such a rectangle existed, or if a rectangle existed, then a Sakari quadrilateral would be a rectangle. And so, in particular, one of the things that's different about hyperbolic geometry compared to Euclidean is that there exist no rectangles at all. So let's see how we would do this. A sketch of the proof. So we'll let quadrilateral ABCD be a Sakari quadrilateral as specified here. We'll let's let little a be the distance from A to B. Let's let BE and CF be the critically parallel rays to the ray AD. So we're going to get a couple of rays that come down like this with points BE, CF. And when that's the case, then we have that the measure of angle ABE is in fact exactly the critical function of A, and similarly we have the critical function of A also as the measure of angle DCF. Now, if we choose another point over here, choose another point G over here in order to make reference to certain angles here, we claim that triangle EBCF is a closed triangle. And that's because we have that the ray BE is critically parallel to the ray AD, and the ray AD is critically parallel to the ray CF. So that means that by Theorem 118, we have that the ray BE is critically parallel to the ray CF. So that means that the open triangle EBCF is in fact a closed triangle. And so, by the exterior angle theorem, we have that the angle FCG, which is an exterior angle to the closed triangle EBCF, has to be greater than the angle EBC. So we have that the measure of angle DCG is equal to the critical function of A plus the measure of angle FCG, which is greater than the critical function of A plus the measure of angle EBC. Now the critical number at A plus the measure of angle EBC is exactly the measure of angle ABC. And we know that the two upper angles of the Sakari quadrilateral are congruent, so the measure of angle ABC is equal to the measure of angle DCG. Sorry, DCB, other way, to get the upper base angles. So what we've shown is that the red angle here is greater than the blue angle right here. However, they form a linear pair. So since the angle DCG is greater than the angle DCB and they form a linear pair, that tells us that angle DCB must be acute. And so that tells us that in a hyperbolic world, rectangles don't exist. In fact, the existence of even a single true rectangle in a geometry is enough to show that you are living in a completely Euclidean geometry, where the parallel postulate holds, and so forth and so on. Now, what this means is that our picture of a Sakari quadrilateral here is not what it sort of looks like in a hyperbolic geometry. A hyperbolic Sakari quadrilateral looks like or looks something like the following. Where we have these sides that appear somewhat curved, but this is what your typical Sakari quadrilateral might look like in the standard Poincaré model of hyperbolic geometry. Now, we used facts about Sakari quadrilaterals back when we first encountered them to prove things about triangles, pardon me, and we're going to do the same thing again here. In fact, knowing that the upper angles of a Sakari quadrilateral are acute allows us to prove that not only do rectangles not exist in hyperbolic geometry, but the sum of the interior angles of a triangle in hyperbolic geometry is never 180. It's always strictly less. That's Theorem 122, which says that given triangle ABC, the measure of angle A plus the measure of angle B plus the measure of angle C is always strictly less than 180. So for the proof, first we assume that triangle ABC is a right triangle with right angle at A. So in that case, we've got a picture that looks something like this. A, B, C. We've got a right angle here. And now we've seen this before. We can let D be a point so that quadrilateral ABDC is a Sakari quadrilateral. So we can choose the point D up here in such a way that the line CD is perpendicular to the line AC, and get a Sakari quadrilateral like this. And we can use this to show that the sums of the measures of the angles at B and C are less than 90. So if the measure of angle ABC plus the measure of angle ACB is equal to 90, then that would mean that angle BCD would have to be congruent to angle ABC. So if the red and the blue angles did in fact add up to 90, then because the other angle down at C also adds up with the red to give you 90, these two angles would have to be congruent. The two blue angles would have to be congruent. So in this case, we would have that triangle ABC is congruent to triangle DCB by side angle side, and so that would mean that the angle at D is a right angle, a contradiction. So it cannot be the case that the red and blue angles together add up to 90. They must add up to less than 90, and therefore, since the measure of angle A is 90, that tells us that the measure of all three angles inside is less than 180. So the measure of angle A plus the measure of angle B plus the measure of angle C is strictly less than 180. Now let's look at what happens if we don't have a right triangle, because the technique of the next proof suggests something that is going to wind up being very important to us in terms of understanding how triangles work in hyperbolic geometry in general. Now, if triangle ABC is not a right triangle, let's let AC be a longest side, relabeling if necessary, and let D be in the segment AC such that the line BD is perpendicular to the line AC. Something we've done quite a few times. So we got A, B, C, D, and now we have that the angle at D, the two angles at D, are both right angles, and therefore we can use the first paragraph to get where we want. Now we have that the measure of angle A plus the measure of the angle at B plus the measure of the angle at C is equal to, we can split up the measure of angle B as the measure of the angle ABD plus the measure of the angle DBC, and then we add the angle of the measure at C. Now, if we look at the measure of angle A plus the measure of angle ABD, that's two angles, the two small angles inside a right triangle. And what we just did in the previous paragraph is show that those two together have to be less than 90. The red and the blue together have to be less than 90. Similarly, if we take the green angle and the yellow angle, that is the angle DBC, plus the measure of angle C, that also has to be less than 90. Because all of the angles inside the right triangle DBC have to be less than 180. But that gives us exactly 180. So this shows that in hyperbolic geometry, no triangle has a sum of interior angles of exactly 180. They all have less than 180. I think of this as more pieces to the all or none principle that we had before. So the all or none principle says that either all lines through points parallel to a given line are unique or none of them are. Either there exists at least, either all Sakari quadrilaterals are rectangles or none of them are. Either all triangles have internal angles adding up to 180 or none of them do. There is no middle ground. There's no such thing as a geometry that's sometimes Euclidean and sometimes not. Now, we can actually use this fact that the sum of the interior angles of a triangle is always less than 180 to define a measure that we attach to an angle known as the defect. The defect of a triangle ABC is defined to be delta ABC, delta triangle ABC, and it's 180 minus the measure of angle A minus the measure of angle B minus the measure of angle C. Because we're working in hyperbolic geometry, the defect of any triangle ABC is always positive because the sums of the interior angles is always less than 180. Furthermore, we have that the defect of any triangle is always less than 180. So the defect is always a number that's there between 0 and 180. In a way, the defect measures how close to being a Euclidean triangle a triangle is. The closer the defect is to 0, the more the triangle looks like a Euclidean triangle. The closer the sums of their interior angles are to 180. And the larger the defect is, the less that triangle looks like a Euclidean triangle. The most important property that we have for the defect is Theorem 124, which says that given triangle ABC, if we take some point D between B and C, then the defect of triangle ABC is equal to the defect of triangle ABD plus the defect of triangle ACD. So if we take some triangle like this, A, B, C, D, this is saying that we can find the defect of the large triangle by adding up the defects of the smaller ones. Now the proof of this is really just an exercise in arithmetic. Let me label these angle measurements here with little x, y, z, little a, b, c. We have that the defect of triangle ABD plus the defect of triangle ACD is equal to, well, the defect of triangle ABD is 180 minus x minus y minus z. And then the defect of triangle ACD is 180 minus A minus B minus C. Combining those together, we get 360 minus, and I'm going to start grouping these up. X and C I'll group up. This is minus x plus c. And then this is minus y, then minus b, and then minus a plus z. Now, we have that x plus c is exactly the measure of angle BAC. Y is exactly the measure of angle B. Little b here is exactly the measure of angle C. And A plus Z is exactly 180 because they form a linear pair. So from this we get 180 minus the measure of angle BAC minus the measure of angle B minus the measure of angle C, which equals the defect of triangle ABC. So the point is that we can look at the defect of a triangle, and it's always going to be equal to the sum of the defects of triangles in a triangularization of it. We'll come back to that in just a sec. But first, let's look at a surprising result. In hyperbolic geometry, there is no similarity theory for triangles. To be more precise, what Theorem 125 tells us is in hyperbolic geometry, if triangle ABC is similar to triangle DEF, then triangle ABC is in fact isomorphic to triangle DEF. In hyperbolic geometry, it's impossible for two triangles to be similar without being congruent. Weirdly, this says that in hyperbolic geometry, it's impossible to truly scale anything up and down, that by changing the size, you change the shape. In some ways, shape and size are intimately related to one another. Let's see why that is. Let's suppose that triangle ABC is similar to triangle DEF, but that segment DE is less than segment AB. Let's suppose that that's the case. Let's draw a triangle here, A, B, C. So now let's let E prime be in the segment AB such that AE prime is congruent to DE. So we've got the point E prime over here. And let's let F prime be in the segment AC such that the segment AF prime is congruent to the segment DF. Like this. And so now we have that since the angle at A is congruent to the angle at D, we've assumed that the two triangles are similar, and therefore their corresponding angles are congruent. So since the angle at A is congruent to the angle at D, we have that triangle A, E prime, F prime is congruent to triangle DEF. So this means that in particular the defect of triangle A, E prime, F prime is equal to the defect of triangle DEF, because all of their angle measures are the same, and that's what defines the defect. However, look what we can do here. We can introduce another line segment here, and now we can consider a number of triangles here. But we have that the defect of triangle ABC is equal to the sums of the defects of the triangles that make it up. It's equal to the defect of triangle A, E prime, F prime, plus the defect of triangle B, E prime, F prime, plus the defect of triangle B, F prime, C. The defect of the whole big triangle is the sum of the smaller defects. We're told that this is equal. We don't know what the defects of the other two triangles are, but we know that the defects are non-zero, which means this is greater than the defect of triangle A, E prime, F prime, which equals the defect of triangle DEF, but we assumed that the triangle DEF was similar to the triangle ABC, which means that all of their angles are congruent to one another, and therefore the defect of triangle DEF is equal to the defect of triangle ABC to begin with. But this is a contradiction. We have that the defect of triangle ABC is greater than the defect of triangle ABC. That doesn't work. We have a contradiction. And so what we have is that if there are two triangles in hyperbolic geometry where all of the angles inside are congruent, corresponding angles are congruent, then in fact the whole triangles are congruent. So in fact, angle, angle, angle is a congruency statement in hyperbolic geometry, not a similarity statement. However, do note that there is no angle-angle theorem in hyperbolic geometry. Our angle-angle theorem that we had before was based on the sum of angles inside a triangle always being 180, which we don't have here. All right, there are a couple results on the critical function, which we can use defect theory to get to. The details of this are in the notes. I'm not going to go through them in detail here. But Theorem 126 tells us that the critical function has no lower bound. Tells us that the limit as a goes to infinity of the critical function is, in fact, 0. Now, the critical function itself is always positive, but this tells us that if we make our lengths bigger and bigger and bigger and bigger, the critical function gets closer and closer to 0. Which means that if we take a very, very long segment here, we could have a ray that forms an almost 0 angle with the ray in the lines in the right angle, and still wind up with a ray that doesn't intersect the bottom ray. Also, Theorem 127 says that you can always find triangles with a defect as high as you like, as long as it's less than 180. The supremum of the defect of all triangles ABC, where triangle ABC is simply a triangle, equals 180. Now again, no single triangle can have a defect of 180, but you can always find triangles that do that. Now the trick to this one is actually looking at small triangles. What we find in hyperbolic geometry is that the smaller the triangle, the smaller the side lengths are, the more it looks like a Euclidean triangle. That is, the smaller the defect. And sorry, this theorem here, Theorem 127, says that you can make the defect as large as you like by making a very large triangle so that the defect is very high. You look very much unlike a Euclidean triangle. But the other side to that is that you can make the defect as small as you like by taking a very, very small triangle. And this is one of the difficulties, as I alluded to earlier, with detecting whether or not you live in a Euclidean universe or not. As a species, human beings measure things on very small distances relative to the entire universe. And so if the entire universe is non-Euclidean, but we're only able to measure things accurately within, say, our solar system, that's not a very big region relative to all of space. And so it could be that on the levels that we're able to work with, the defects of all the triangles with side lengths, only a few light years, are very, very close to 0, and we can't detect them. All right, the last thing that I want to mention is that we can actually use defect in order to define a kind of area function. And this was hopefully suggested by some of the things that we were doing earlier, where the defect of a triangle is the sum of the defects making it up. Theorem 128 makes this reasonable. So for a triangular region Ti, where we define triangular region exactly as we did when we talked about area before, for a triangular region Ti, let the defect of Ti be the defect of the triangle ABC, where triangle ABC is the boundary of Ti. We use sort of similar notation for defect and for boundary, but I will try to make sure that they're distinct from one another. And for a region R with triangularization, R equals the union of a bunch of TIs. Let's let the defect of a region be the sum of the defects of the triangular regions making it up. Then this defect function expanded out to arbitrary polygonal regions is an area function, i.e. it satisfies the conditions A1 through A4. Now, it's sort of a weird area function. It doesn't seem like it directly takes into account like the side lengths of the triangles, but it sort of indirectly takes it into account. As we mentioned before, when if we have small triangles, then the sums of the angles inside are going to be very close to 180, so the defect's actually going to be small. Whereas when we take large triangles, they tend to look more like this, where the angles inside are kind of narrow and skinny, meaning that their sum is a lot less than 180. Triangles like we have on the left have small defect and hence small area, while ones on the right have a large defect and hence large area if we define the area of a region in hyperbolic geometry in terms of the defect, which is kind of what we have to do, because a lot of the statements that we had about the products of altitudes and bases being constant all heavily depended on a robust similarity theory for triangles, which we don't have. And so we can define area in hyperbolic geometry. It's definitely a little weirder, and because we don't even have squares in hyperbolic geometry, it's a little bit more difficult to interpret exactly what area is. However, it can be done, and that it just goes to show how there are lots of things that can happen, lots of geometries out there that behave very, very differently than the Euclidean geometry. Hyperbolic geometry is one of those such geometries. I should mention that there are also others that fail to satisfy some of the other axioms. Once you have the axioms up through side angle side, you either have to choose, or am I going to have the parallel postulate or the hyperbolic parallel postulate? One of those has to be the case. However, there are other geometries, such as projective geometry, which eliminate some of the previous ones. Some going even all the way back to some of the initial incidence axioms. Some of those can be dropped, and you get other interesting geometries, but that's outside the scope of this course.